All right, I think we're ready to go. I think I'm streaming to all the things. All right. Make sure. All right. Why does it keep cutting out? Stop doing that. Darn it. All right, let me just take one more. Okay, everybody, let's hope this works. Hi, everybody. Welcome back to Telescope Talk Pro as I bang the microphone all over the place. My name is Tony Darnell from deepastronomy.space, and I have a feeling we're going to have an interesting day. My streams don't seem to be playing nicely. Please let me know if you guys see it drop out, and I would appreciate it. Otherwise, I'm recording this locally. Hopefully, we'll be able to not need this local recording. Anyway, welcome back to Telescope Talk Pro. As I said, my name is Tony Darnell, and I'm from deepastronomy.space. And today we're going to be talking with people from the Large Millimeter Telescope, and that is a telescope that is located in Mexico, and it's one that we haven't ever talked about before. So I'm really excited to have people on board to give us a glimpse into it. It was also one of the telescopes used in the collaboration for the Event Horizon Telescope, which most of you may have remembered had made a lot of news recently with their release of the black hole image in the center of the galaxy M87. So we'll talk briefly about that just a little bit, but mostly we're going to talk about the telescope, the kind of science that's being done there, and what some of the facilities are like, things like that. So I want to let everybody know that Telescope Talk is sponsored by OPT Telescopes. They are a world leader in telescopes and accessories for both amateur and professional astronomers. I want to thank them for their support of this hangout. I am streaming, I hope, on Twitter, Twitch, YouTube, and Facebook. Now, I think I can do. It says that people are watching on Facebook. So I'm looking at the live chat, hopefully, from all of these things. Ahmed Abdullah is on Facebook, as well as Dennis Van Houwermeiren. Did I do that right? Anyway, they're coming in from Facebook, and that's a new ability that I have because Facebook has recently not played nicely with these restreaming capabilities that I have. So welcome, everybody. Hopefully, you guys will ask us questions on the chat. So, what am I doing here? Let me bring up my guests. Here we go. Joining me, right next to me, over, I knew I'd get it wrong, this way, right there, is Nat DeNigris. She works at the University of Massachusetts at Amherst. And right down here is David Sanchez from the Large Millimeter Telescope. And David, you are down there right now, aren't you? You are down out on the facility.
Yeah, I am right now at the LMT base camp, located roughly an hour away from the telescope site.
Oh, okay. And now, for those of you who don't know, a lot of these observatories, I mean, I've been to a lot of observatories around the world, and they tend to have these facilities where the where the astronomers stay and the housing and all of that kind of stuff is in a slightly different area than where the observing is taking place. So, for example, in Chile and at the CTIO there in Cerro Tololo, they have a set of apartments there that if you sleep during the day, which most astronomers do, they have these heavy duty blinds that come down and close off your entire apartment, so you don't even know that it's daylight out. Do they have that there? I mean, I can see that you're in daylight now, David, but do they have those abilities there where you can just shut off all the windows and stuff?
Yeah, we have some kind of a special blockout curtains that basically allow us to have a dark room during the day.
Ah, okay. All right. Well, where in Mexico is the LMT?
Okay, probably if you load up the slide 3, the LMT slide 3 location.
LMT slide 3. Okay, let me go. Oh, they're not in order. Darn it. Where are they? Here it is. Ah, there we go. Okay, I've got it up now.
So this is basically a map from Google Maps saying where we are roughly 260 kilometers away from Mexico City towards the Gulf of Mexico. And we are, the base camp is located in a town called Ciudad Cerdán, which is the largest, let's call it city in the area. And the telescope is located at the top of Volcán Sierra Negra, which is translated to dark, the dark volcano or the black volcano. And if you bring up the slide number 2, no, slide number 4, sorry.
Sorry, number 4? Okay.
Yeah.
It's up now.
So you will see that we are next to the tallest volcano or mountain in Mexico, which is Pico de Orizaba. Actually, this is the third largest mountain in all North America. And just towards your right, you will see a small cospitting on the top of the Volcán Sierra Negra. That's the LMT seen from Cholula, roughly 150 kilometers away from the site.
So LMT is on Volcan Sierra Negra then?
Yeah.
Okay, and that's at 15,000 feet, 4,600 meters. And wow, Pico de Orizaba is huge. Look at that, 18,000 feet.
Yeah.
Wow. I grew up in Colorado, and we have a bunch of 14,000 foot mountains that people like to climb. I only climbed one, but that's that's short compared to both of these. So that's pretty amazing. So this is where it's located. Is there anything specific about this location that was necessary for the kind of science that it does?
Well, you usually want to have your telescope, particularly sub-millimeter and millimeter telescopes, you want to have them as high as possible and on places that are as dry as possible.
Okay.
That's because for us, the atmosphere is not totally transparent as is in radio waves or in optical astronomy. So it's partially transparent.
Okay, great. So I'm going to go into this a little bit. The large millimeter telescope, what is the wavelength range here?
We are observing between 815 microns and 4 millimeters.
And 4 millimeters?
Yep, that's the highest energy of the microwave.
So 815 microns, that's the infrared, isn't it?
It's far infrared.
Far infrared, right.
Yeah.
And so you can, which explains why you need to get high in the atmosphere to get rid of the water vapor. But I didn't know that that the atmosphere got in the way of radio waves at this wavelength. So apparently it does.
Yeah, this is this atmospheric window we have is slightly different from the radio window. We have lower frequencies like the Wi-Fi or the BLA window, which is roughly around a few gigahertz. We're operating at hundreds of gigahertz. So we are, in some way, we're far away of the radio part of the electromagnetic spectrum.
You're far away from it, you say?
Yeah.
Okay, I always have a hard time going back and forth between gigahertz and wavelength.
Yeah.
I know you can do it by multiplying, dividing by C and getting all that.
So For example, usually BLA, the most famous wavelength is 21 centimeters, which
Right.
is the
And
transition of the neutral hydrogen. And for us, it's basically 100 times larger wavelength compared
okay.
to the observations we're doing.
Okay.
So it's a slightly different regime. Our telescope look very similar to a radio telescope, but is built in a way that is um, efficient to capture this 1 millimeter wavelength radiation.
One it's best at around about a millimeter, you said.
Yeah, it's, it's,
Okay.
it's the best around 1 millimeter.
Okay, so just so that I can see how this fits in with the picture of all the other telescopes, ALMA is a millimeter. Okay, that makes sense. It's in the name, millimeter and sub-millimeter band telescope, right? So they look at things smaller than 1 millimeter as well, which allows it to see things like gas and dust and other kinds of materials that you can't see in optical wavelengths, correct? Or at least it lets you see through these materials, because that's what allowed people to see black holes at the center of our galaxy as well as M87. So these are important wavelengths, but they don't overlap, do they? What you do at the large millimeter telescope is not the same as what they do at ALMA. There's not overlapping wavelengths, are there?
Yeah, we have an overlapping wavelengths. ALMA, basically the band 6 and 7, if I recall correctly, correspond to a few millimeters. So we have some sort of overlap on the wavelengths we are observing with ALMA. And that's basically, that's why we can combine ALMA and LMT baselines for the EHT observations to provide an image of the shadow of a black hole, just
Okay.
because we have that overlap. We both observe at the same time at the same frequency.
Okay. And what are you looking at now while you're down there?
Well, last night we were testing a new receiver we received last year. It's called Sequoia. It's an spectrometer that can both produce images and produce a spectra of molecular lines in galactic star formation regions. Its name is it's Sequoia is operating at the 3 millimeter wavelength.
At 3 meters, you said?
Yeah, three
Okay.
millimeter wave.
3 millimeters.
Yeah,
Okay.
the
Right.
3 millimeter atmospherical window.
Okay. And so you're interested in
Actually,
star formation then?
yeah. We with Sequoia we trace the molecules that are in the interstellar medium and that are associated with the star formation regions.
Okay. All right. Okay. Well, Natalie, let me get you in on this a little bit. Nat DeNigris, what are you doing as part of the team, and what kind of astronomy are you interested in?
So I do something a little different. My background is in engineering, and so I do astronomy instrumentation. So I'm working on a new facility instrument for the LMT called Toltec, and it is going to be a follow-up to a previous camera there called Aztec.
I see a theme going on here.
Yeah.
So what kind of camera is Toltec?
Toltec is going to be a millimeter wavelength camera, but it will be able to image in 3 separate wavelengths and also do 2 polarizations simultaneously. So we have 3 focal planes of detectors all on 1 optics bench.
Three focal length. Hang on. Say that again. 3 focal length detectors on one.
3 focal planes of detectors. So if you pull up the picture called cold optics, I think that kind of gives a better overview of what I'm talking about.
Okay, I'm just looking for it now. Cold optics. Oh, there it is. Okay, I got it up. Okay, let
Awesome.
let me get it up. There we go. Cold optics is up. So yeah, this is what you're building.
Yeah, so this is the inside of Toltec. There are 4 different temperatures that we were working with, but this is just showing the 3rd coldest stage, which hosts the different optics we're looking at. So what you see are different mirrors, things called dichroic splitters actually take the light and split it off into different frequencies and wavelengths. And so we have a 1.1 millimeter band, we have a 1.4 millimeter band, and a 2 millimeter band. And so we'll be able to capture information from the sky in all three of these wavelengths at the same time.
And they will all appear on the focal plane at once.
Yeah.
And the advantage of that is so that you can get simultaneous observations and wavelengths all in the same data set, right?
Exactly. And it's actually going to be great for removing systematics from different observations. So say you're looking at a galaxy cluster, there's a certain effect where the cosmic microwave background will go through the galaxy cluster, and this is called the Sunyaev-Zel'dovich effect, and it heats up the cosmic microwave background you see. But in the three wavelengths we'll be able to image with Toltec, you can separate out these where it's heating up. And so you kind of can remove effects from atmosphere, you can remove effects from just background noise from this effect on the sky. So it's going to be really great for millimeter wave like astronomy in that way.
Okay. Well, help me understand the data then that come out of these telescopes, because whenever I hear about radio telescopes, it's usually a time series of frequencies that come out, and it's not an image, although they do build images from the data. But what you get from the telescope isn't an image. Like ALMA can make an image, right? But you have to combine all these radio signals together in a way that, and then convert the data into something that resembles an image. Is that what's going on here with the LMT, and in particular with Toltec, or is it something like something different? Like, are you actually getting an image?
So we're going to be taking time streams. So the detectors we're using are unique. They're a newer form of detector called a lumped element kinetic inductance detector. And let's
say that slower. A what?
A lumped element kinetic inductance detector, or lovingly called LKIDS.
Okay. Lump element. A lump element. Okay. Keep going then.
So the kids have taught us a lot about patient parenting. But they are, if you took an intro physics class, you might remember an inductor and a capacitor in a circuit. It's basically that, except the thing that's absorbing the light is your inductor. And these circuits have a characteristic frequency that they respond to. So if you send in an electronic signal at that frequency, you can detect a drop in power from our readouts. So if we do that for 4,000 detectors on one focal plane, what we're getting out from a time series is light is absorbed by that inductor. It changes the property of the inductor, so its characteristic frequency changes. But since we're only sending in an electronic signal at the original frequency, you end up reading out a time series of just fluctuations at that one point in time. And then you can back that out to figure out a map for each one of the detectors looking at the sky. And so we're kind of getting images from that rather than just taking a picture like you do on your cell phone.
Okay. Well, how did you get into this? How did you get into have you always been more interested in engineering than, say, science, or did this, I don't know about you, but my career went like this, and I'll just say it very briefly. I started as wanting to be an astronomer, a PhD astronomer, but I didn't want to go to grad school. I got a physics degree, a bachelor's degree in physics, and then I graduated. I had a young family, so I said, graduate students, I can't be that right now. So I went into programming, and I learned I got computer programming, and learned from there that I really enjoyed writing code to process data, get reading cameras, reading camera data and things like that. But I never planned on doing that. Tell us a little bit about how you got where you are. Was it something you always knew, or did you kind of, I don't know, follow a yellow brick road until you just sort of ended up there?
Definitely the latter. I think my parents are watching, but they're both artists, and so I started in art myself in my freshman year of college.
Oh, you started out in art. That's
Yep,
great.
and I accidentally took a physics class.
Oh, yeah. Well, how do you do that? How do you act? Oops. I took a physics
My
class.
friend signed me up for the class without telling me, and so
I love it. Oh, what am I doing in here? What is this?
it was just like, just show up at this time and place. But the very first day of class, the professor did that experiment showing that a penny and a feather can fall at the same rate in a vacuum tube. And I was just like, wow,
Oh, yeah,
how
yeah.
can you explain all of that with math? And so I ended up doing physics for my undergrad and psychology on the side because I couldn't decide for a while. And in the process, I ended up doing an internship at NASA Goddard Space Flight Center in Maryland.
Oh, yeah.
And there, and I still do this work now as a Pathways intern, I build detectors for X-ray space telescopes. And that was the first time I realized that, wow, I really enjoy building things. And I kind of want to keep doing this for observational astronomers. And so I kind of ended up there. My boss at Goddard was roommates with the person I ended up doing my first year project with here at UMass. And so I've continued to work on Toltec as my project, and I really enjoy building things.
Now, I've always told people, sometimes I give advice to people who want to start out their careers, and you guys can both tell me what you think of this, but I've always said that if you can build things or program things, that there will always be jobs for you in astronomy, because there's no shortage of people, of astronomers out there making models and making predictions. What we need are people who can build a telescope or put together a camera like you're doing, Nat, or, program it to process the data or take the images. So I've always said that is a growth industry in astronomy. Would you guys agree with that statement?
Yeah,
Dave?
actually, my background is I came from computer science. My major is in computer science, and then I decided basically to go back to astronomy, just having all the knowledge of programming code and building tools to analyze data, and then put it into work for the telescopes here, in particular the LMT. And much of my PhD thesis is developing this kind of codes to analyze the data of cameras like Nat is building, just to produce images that are more accurate to the real emission of astronomical objects.
So, David, it sounds like you took a path similar to mine. You came at this from a programming perspective and decided that you could write code to process and analyze these data. And am I right? Is that what you just said? That's sort of how you got, and now you're doing research astronomy. So how did you make that leap? How did you go from being a computer science software person to getting involved in the LMT and now doing observations?
Well, when I finished my bachelor degree, I realized that being at an office, just working in regular office hours, was not for me. So I came back to my passion as a kid, which was astronomy. I had plenty of books of the stars, the planets, the solar system.
It always comes back to that. It
does.
does.
I was an astronomy geek when I was a child. So, and it happened that the LMT was being built at that time. So I learned about the LMT, and I said, I want to work there, and just moved to the National Institute of Astrophysics and started studying there. Learn general relativity and quantum mechanics just to be able to model the data we were working. And that's basically my motivation. I wanted to be an astronomer since I was a kid.
So and this telescope is located in Mexico, and I do a lot of hangouts about a lot of observatories around the world, and I'm not familiar with all that many telescopes in Mexico. How many other facilities are there that you guys know of that are in that country? And is Mexico a good spot to do astronomy?
Well, we have a few other small optical telescopes, particularly the National Institute of Astrophysics, which is the institute that is involved in the LMT project, has another telescope in the northern part of Mexico, but it's a small 2-meter telescope. It's called the Guillermo Haro Observatory. And people from the National University of Mexico, or UNAM, they have a few telescopes in the Baja Peninsula. Uh, I think those are also 2 and 4-meter telescopes.
Okay, now as you're describing this, I'm playing this movie that you sent me. I believe it was Nat, the one GTM construction.
Yeah, I think so.
I'm just showing that now as it goes. I guess I never really thought about it, but to me it seems like Mexico would be a pretty good site, especially if you've got some high mountains. Now, Chile, unfortunately, has you guys beat as far as the driest desert in the world in Atacama. But there's probably some really good sites throughout Mexico where you could locate a decent observatory. So. So this is one. So this is and you're saying this is probably the largest in Mexico. Then is that right?
Yeah, well, the LMT is probably one of the most largest scientific projects in Mexico. It's just a huge endeavor for ourselves.
And what's the feeling in the country? Is this something that you feel like more people want to get involved in? Is there an interest in the country for doing more of this?
Well, it's kind of. I think that right now that we got these results from the EHT, that plays an important role into motivating people to come to begin observations or try to get an astronomy or an IT degree involved into astronomy. So I think we're getting there. We haven't got the best publicity around Mexico, so that's a down on us. But I think it's changing. I think right now people is realizing that doing these kind of projects in Mexico it's possible.
Okay, let me. I'm getting some questions here. Let me scroll back up on some of the YouTube questions so I can get to the beginning. Adam Synergy wants to know. Hi, Adam. By the way, I haven't seen you in a while. It's good to have you back. At such high elevation, is snow and ice buildup on the dish a problem?
Yeah, it is.
It
It
is.
is, but usually through October through May, we have a few snowstorms. Fortunately, the temperature at the site usually varies between a few degrees above 0 degrees Celsius and below 0 degrees Celsius. So we are able to melt during the day all the ice and the snow that builds up into the dish.
Okay. And I don't understand this question, but I'm going to ask it anyway. Hans Milling is asking, are all radio telescopes single aperture to not distort the radio waves?
Could you say again the last part?
Are all radio telescopes single aperture to not distort the radio waves? I guess I'm thinking a lot of radio telescopes are multi-aperture. I mean, the VLT is, the VLA in New Mexico is a good example. So they put those together with interferometry. So I think that they don't distort the radio waves, do they? Do single aperture telescopes distort the radio waves?
Well, we can. I mean, if you have multiple aperture telescopes, you need to basically store those radio waves in some way through probably some kind of detector, and then you correlate those and look for the delay times in the information from astronomical objects to build an image or a spectrum of the object you are looking at. So I think all the radio and millimeter wavelength telescopes, we store in some way a representation of the light we're receiving from outside the planet.
Okay. Yeah, and following along those lines, I mean, because of the nature of radio telescope data, maybe he's talking about things like diffraction. I'm not entirely sure, but diffraction of these radio waves isn't as big a deal, as I understand it, as it would be in the optical wavelengths. So building larger apertures it's more convenient or easier to do with radio telescopes than not. Which brings me to the EHT. You guys were a member of the EHT collaboration, right?
Yeah.
What were you? Did you just provide? So tell us how that worked. I mean, we know that what they used interferometry to gather the light from all of the different radio telescopes that were in the collaboration from around the world, one of them being Mexico, one of them being your telescope. Did you have to precisely coordinate your observations with everybody else's? How did that work?
So basically, you need to build up a schedule of the objects you are going to observe and coordinate among all the sites, among all over the world, to be observing at the same time the same object. Moreover, you need to, when you store your data, when you store the millimeter wave emission, you need to tag it precisely with a timestamp. So later you can recombine it with the data of other telescopes.
And that was the key, right? That timestamp couldn't just be something you read from a clock or what your computer did. It had to be like atomic clock good, right? Do I understand that right? I mean, you needed to do it to like a cajillion decimal places because when all of that data came together, if you just add it all up, then you just get, more signal and your noise adds up. But to get the resolution required from long baseline interferometry, those timestamps needed to be matched. So you said, okay, here's what Chile took, here's what the LMT took, and if you add and you process them somehow in parallel, you don't add them, you collect them as if you match up their timestamps, and then you get two signals from two different parts of the world that add up in a way that the resolution is higher. And that's about all I can say about that. I may have just screwed that whole thing up.
That's a good picture, yeah. So basically what you do with interferometry is you are looking to the time delay of the light as it gets detected by different telescopes. So if you want to do an image, you have to be really precise on this time length that took from, let's say, from Chile to Mexico for that same wavefront to arrive. So basically, if you are able to use, we're using an hydrogen maser as a plug source, and GPS coordinates to also have the exact location, or within a few centimeters, the exact location of all the telescopes.
Yeah.
When you have the exact location at this precise time stamping, then you can locate for these small amounts of delays between telescopes. And in those delays is where you can basically reconstruct an image with a higher angular resolution than the individual telescope by themselves.
Yeah, I'm still having trouble visualizing how that works, but over time, as I talk to more people like you guys, I slowly get it. Interferometry can also be used to cancel out light. Like if you're looking for exoplanets, you can use it to cancel out the light from a star to see the planet better. But in this case, the way I always look at it is that if you imagine a big mirror, just a regular reflecting spherical mirror, and every point on that mirror contributes to its resolution capability because it's a function of its size, then you can think of this telescope, the EHT, as every location around the world is a spot on a mirror bringing in a data signal. And because of the way resolution works, it's the wavelength is a function of the wavelength and the diameter, then you get, as you say, you put it together in a certain way that you keep the resolution capabilities intact while still getting the signal. If you don't picture that, folks, don't feel bad. I don't either. I'm still struggling with it, but that is in very simple terms how the EHT worked. And Radio telescopes, they do this all the time just because I guess the wavelengths are more conducive to this kind of thing. I don't hear, there are some interferometry being done with optical telescopes, specifically at ESO, and I think it's Paranal. They have the unit telescopes there. But mostly, it's done with radio telescopes that I always hear about.
Yeah, and it is easier to do it in the radio telescopes than you have to do optical interferometry. Basically, you actually have to interfere two different wavefronts of light at the same time. Where with radio interferometry, basically you can store your data, send it to the US or to Germany, and then analyze it. You don't need to have this instantaneous ability to do the interferometry patterns as optical telescope does.
Okay, well, let me go ahead and ask Hans Milling's second question. He's asking, dichroic filters are used to filter light, but when you call the telescopes radio telescopes, is it still light you observe? When people say radio telescopes, I think of AM, FM radio waves. So do you still think of this as light? It is light. It's just
so from the radio waves all the way up to X-rays, that's all types of photons. So it's all still light. Even if we usually think about our car radio, we're receiving photons.
Yeah, and there are brightness levels. Things are, if you look at, say, a nebula in radio, this may not be the best example, but let's say a nebula is emitting radio waves, and then certain parts of it might be brighter than others over the span of the nebula. So you would see stronger radio signals and you'd see fainter radio signals, and when you put all that together, you get a radio picture of the nebula. I wish I hadn't used nebula, but it's all I can think of right now. They don't really generate a lot of radio waves, but stars and black holes and galaxies and neutron stars, all these things do emit, and these are generally point sources. But you can, if you looked at an extended object in radio waves, and if it was emitting in radio waves, you would see a radio picture. You know, you'd have to convert it into brightness like this one. Let's say you looked at it in 1 millimeter. Our eyes don't see 1 millimeter, but you see, you get different brightness levels from your detector, like the one, like Toltec, for example, the camera you're building, would show various levels of brightnesses in the wavelengths that it's looking at and construct a picture, wouldn't it, from the detector?
Yeah.
Right. So you've got a detector that's sensitive to the wavelength you're looking at. By the way, what's it made of? What detector are you using?
I thought you'd never ask.
Huh? You thought I'd never ask. You have pictures too, don't you?
Detector science. It's amazing. So these are a trimetallic sandwich of superconducting metal.
Trimetallic sandwich of superconducting metal. That sounds like a rap song. That's awesome.
I know.
Yeah.
I'm in a band with my collaborators, so.
How are you? Well, you do it all. You do it all, Nat. Okay, well, I'm showing something called Detector Assembly. Is that what you're working on?
So these are made by our collaborators at NIST. And so they've made the kit array that you see in the bottom, and then the feed horns that guide the light to the array. But if you look in the lower right-hand corner, you'll see a little picture of what is a single pixel.
Okay, hang on. Let me make sure I've got the right one. I'm showing Detector Assembly. That's not it.
I think so.
In the lower right-hand, there's nothing there.
Okay.
So how about... Is it NIST slide? Is it that one?
Oh, if you look at detectors, yeah.
Oh, detectors. Okay, there it is. Got it. It's up. That's what I had up at first. Okay.
So if you look in the little lower right-hand corner, I think that's a detector assembly that you have up right now. But there should be a picture of the detector, like. So a single pixel on the focal plane is made up of 2 detectors, and it looks kind of like a plus sign with 2 big rectangles next to it. So that little plus sign is actually where we absorb the light.
Okay. We're still looking at detectors.png, right?
Yeah.
Okay. And the plus sign is where?
So if you look maybe it's on my right, your left. But so right next to where it says liquid array, there should be a little box that shows
Transmission
a
line.
picture of a detector.
Yeah, and that's called transmission line, right?
Yeah.
Okay. And that,
so
that plus sign. Okay, I see.
Yeah, so that little
Okay.
tiny plus sign is actually our detector element. It absorbs the light from the sky.
At what wavelength again?
This is for the 1.1 millimeter, but we have the 1.4 and 2 millimeter.
So there you
bands.
go. That little plus sign is a radio pixel, isn't it?
Yep.
There you go, Hans. Check that out. So you and if you array these pixels like you've done in that thing on the, is it on the left? Is that what it is?
Yeah. So the middle one shows a full array.
Okay, so that's the full array, not feed horn, but the liquid array.
Yeah.
Okay, so that's the chip. That's the CCD array with. It's not a CCD, but that's full of those plus signs, and those plus signs are what detect the radio frequencies.
Yes.
And that is what generates your image, Hans Milling. So there you go. And this is awesome. So presumably what I just said about a nebula, which I wish I hadn't said, but I did anyway, so we'll follow along with the example. You're looking at an extended object with this. Each pixel might pick up varying brightnesses in the millimeter wavelength, and you get a picture.
Exactly.
And this is, how many, is that it? 4,012 pixels?
I think it's back down to 4006, but it's on the order of 4,000 pixels.
And is there in light in CCD world where you've got, you got to worry about the band gap of silicon and stuff to create an electron. Is there a quantum efficiency associated with these, or is it pretty much all the light that falls on it gets recorded?
There's a quantum efficiency, but I can't remember it offhand. There's a really good paper that was written by the PI at NIST. But these actually work using superconductivity. And so they absorb the light and it breaks apart the charge carriers in the superconductor called a Cooper pair. And so that's how these ones work.
Are these superconductors cooled?
Yes.
Okay.
So that was my first year project, was actually building the bus bar system to cool down these detectors. So the inside of Toltec, where the detectors live, actually gets colder than space itself. It gets all the way down to a toasty 100 millikelvin.
100 millikelvin?
Yep.
Wow, that's colder than JWST is going to be when it launches.
Yeah.
That's really cold.
It is very cold.
How do do you use liquid helium, or what do you use to get that cold?
So if you, let's see, I'm trying to think of a good picture. I guess bus bars, O2 bus bars might be a good picture for this.
Okay, I've got it up.
So we use something called a dilution refrigerator. It uses helium, but it uses a mixture of helium-3 and helium-4. And so it does this really neat trick where it evaporates helium-3 from the surface of a mixture of helium-3 and helium-4 to carry away heat from our system. And so if you look in the back, our refrigerator is that white tube that some of my coworkers are working on. And the gold that you see towards the foreground are the bus bars that carry the heat away from the detectors around the entire system.
And how long does it take to, I'm thinking back, I know, I don't know how far I can take this comparison, but when I think about a light CCD chip, I think about readout times and things like that. Are the readout, does it take a while to read out 4,000 pixels? Or is it pretty instantaneous?
What's actually pretty neat is that this technology, the kinetic inductance detectors, they can couple really easily to transmission lines. So you can have 500 detectors on one transmission line. So for the 1.1 millimeter band, for example, we only have 7 transmission lines for 4,000 detectors. And so those are handled by 7 separate computers. And so readout should be pretty fast, but I think David can probably speak a little more to that. He's been working a little more on the pipeline.
David, is that true?
Yeah. Well, I'm working slightly on the Toltec pipeline. So basically, what we record, as Nat was saying, each detector has a different characteristic frequency. So you basically add up all those frequencies, and then you bring it out them of the cold parts of the instrument, and then in electronics and really fast electronics, you filter a specific section of in frequency. That's how you regain the information of every each and one of these detectors. So basically, it's just pulling. You're like tuning your radio. You're tuning your code to analyze the first detector. Then you switch the frequency. You tune to the next detector, and so on. And that's how you transfer from a single transmission line to thousands or hundreds of time streams of different positions in the sky.
Okay. Well, I want to move a little bit to the science because I'm running out of time and I want to talk about what you can do with this stuff. Now, when I was in college, it wasn't I didn't accidentally stumble on physics like Nat did. I love that story, by the way. I'm like, I accidentally took a physics course. I'm going to have to remember that. But the back when I was studying all of this stuff, all my instructors would say the future of astronomy. This is like the mid 90s, early 2000s, or the late 90s, early 2000s. And they would say the future of astronomy is in the infrared because that's where we haven't looked far that much of, and all of the really interesting things are really far away, and they've redshifted. The distant galaxies have all redshifted into the infrared, and that's where they all are. And detectors had just started being sensitive to the infrared. They could build Mercad Telluride chips, and the infrared was starting to open up, albeit in space because not a lot of places on the ground could do it. But it seems to me now, with ALMA coming online and the large millimeter telescope that you guys are a part of, that radio astronomy seems to be really making a contribution. Not like the fuzzy images we used to see back in the day, of like a pulsar or something, but we're getting really high definition radio data now. So what kind of science does that open up for us that perhaps wasn't open, say, 10 years ago or 20 years ago?
Well, if you bring up the slide 6, LMT slide 6, science.
Slide 6?
Yep.
Let me find slide 6. I thought these were in order, but they are not. Let's see. There it is. Okay, I got it up now. Sorry it took so long. Okay, slide 6 is up.
So basically, what we are observing with the LMT is, or in the detectors like Nat is building, is the continuum emission from dusty star formation regions. Those star formations are cold. There are a few kelvins in temperature. They are usually heated by massive stars, and the massive stars produce a lot of ultraviolet and optical light, and it's absorbed by the gas and dust surrounding these regions, and then is re-radiated in infrared and millimeter wavelengths. So we have the opportunity to basically, if you see down to the right, you will see an image from the EHT optical and near infrared camera, and you will see this is a really common object. This is the Horsehead Nebula, and basically you can see that there is not much information of inside these dusty regions or star formation regions that you can retrieve from this kind of images. But if you go to the millimeter wavelength, particularly with Aztec, which is the previous camera of for Toltec, or the previous technology camera, you can see inside these star formation regions, and basically the levels of brightness are indication of how much gas is being converted into stars. So what you want to analyze is how the structure formation, the galaxies, the stars, the galaxy clusters are formed with the cosmic time, and the millimeter wavelength observation provide a unique tool to trace these kind of phenomena, because you are able to go basically up to redshift 10 or back to the dawn of a star formation, and basically you can see objects, provided that they have some kind of dust blocking this emission from stars. You can see those objects really, really far away, and you can trace how the universe started to create more and more structure in more complicated and massive ways. And also another kind of detectors we have, they're not able to produce only images, but also analyze the light spectrum of these objects, and then you can derive these low energy molecular transitions that usually are not available in other kind of an optical telescope, just because the light that these stars produce is able to break down these molecules. So in the millimeter, you have the ability to trace very complex molecules like organic tracers and particles that basically made up us as life forms. So that's the ability we have. And if you can bring up the next slide, the slide 7, LNT slide 7.
Okay, it's up.
So you can see that this is all the kind of objects we can observe. We have dust grains in the leftmost section. You can observe comets or asteroids just to see characterize the light curves and see which molecules are being able to survive in the tails of comets. You can look out for debris disk or traces of other planetary systems in another stars. As I was saying, you can also trace the structure formation and the star formation rate of the universe in basically our galaxy or in a really, really far away galaxy. And you are not limited to that. You can also look to the CMB anisotropies that, like Nat was saying, the Sanchez effect is one that is basically providing you a tool to trace the most massive structures in the universe, the galaxy clusters. These are basically the metropolis of the galaxies, just concentrations of thousands of galaxies in really, really small volume. So this is all the science we can do with the LMT and its different instruments.
Wow, look at that. That's amazing. So in the lower right, where you've got the CMB, right next to it is a radio image. Is that right? Of the same?
Right to next to it is a simulation of set of galaxy clusters, and you are seeing basically what Toltec will see in 1.1 millimeter if it will do a survey
Okay.
around some specific region.
Okay, I want to go back to slide 6 for just a minute. This is beautiful, by the way. This is a beautiful example, and it sort of dovetails with what I was talking about just a while ago about nebulae. Here you've got the Horsehead Nebula, a nebula that is lit up from behind, and
From
there
inside.
are
It is light up from inside.
well, okay, from inside, but it is illuminated from. It's not letting off light itself. It's illuminated from inside or behind and backlit. The and you can see it in infrared and optical, as you can see in the left panel, and then there it is in radio wavelengths at 1.1 millimeters, and that is where the stars are, right?
Yep.
So you can see directly, and imagine if we had a more higher resolution image. I mean, it's just getting better all the time. Nat, can you see this picture? Are you looking at slide 6? Okay. This is Aztec. What will Toltec do that's different than this?
So Toltec is going to have a higher resolution, but more importantly, it can map out this image a lot faster than Aztec could.
Okay. So readout time will be a lot quicker.
Yeah.
Okay, and there you go, right there. That's it. To me, that is the money shot. That's huge because it tells you a lot right there, in terms of where the stars are, where the star formation is. Presumably, you could do something like this with the Orion Nebula too, couldn't you, David? And
Yeah, you
see
can
the
do
stars.
this. I mean, the other advantage of Toltec is that it is able to map larger areas than
Okay,
Aztec. So we quantify this with a number called the mapping speed. So uh, Toltec is going to be, if I recall correctly, and that can correct me, is 30 times faster than Aztec.
and why is that?
And
Why is a faster readout so great? I mean, just more data.
so first of all, it has a lot more detectors. Aztec has only 144 bolometers. So it's a really small array
And
compared
Toltec
to
has
Aztec.
4,000.
Yeah,
Yeah.
it's 1,000 and it's 3 different wavelengths, and Aztec is just a single one.
Okay.
Moreover, Aztec was used as a first light instrument when we have only the inner 32 meters of reflective surface. So its resolution and collective power was smaller than Toltec, which is going to be coupled to the full 50-meter telescope. And then it will be able to gather more light and be more sensitive to this kind of emission.
Okay. All right. Well, I got to get to a quick question here from Upcycle Electronics, and maybe this is a question for you, Nat. I don't know. What's the iterative process for developing telescope hardware, like new sensors and hardware? The iterative process for developing telescope hardware.
That's a good one.
You think you get? I think I understand it, but I'll give you a shot. Go ahead.
Yeah, I think what they're trying to get at is how do you start from maybe just an idea and work your way up. So I came into this project last year, and they had kind of been working on it for a year before I got here for the building and design aspects, but even the concept of it went back to when they had Aztec. And so I think everything's kind of circular. We kind of build on old technologies and try and improve and iterate on those. We knew what Aztec's capabilities were with the 32-meter LMT, and now with the 50-meter LMT, we can, improve on the images we had taken with Aztec and put on a camera that can really capture the full abilities of the LMT now. And so I think, starting with also some just large goals on what you even want image. I think Toltec's going to be really cool because we're doing public surveys that the data is going to be publicly released, and they're going to be in 4 kind of different astronomy themes. And so there's kind of something for everyone there.
Okay, let's drill down on that a little bit. Where are these data going to live? Are they going to be on a portal somewhere people can get access to?
They're going to be through the Toltec website, I believe, but they will be publicly posted shortly after they're collected, I believe.
And when you say it's going to be themed, it's going to be like what? You're going to look at nebulae or galaxies?
So right now there are 4 themes that have been defined by the public, and so 2 of them are galactic based. So there's one called clouds to cores and another called fields and filaments. And so clouds to cores is looking at star formation in local clouds. And then fields and filaments looks at magnetic fields in these filamentary structures we see within clouds. And then the 2 that I'm mostly interested in are the extragalactic, the really far away stuff. We're doing one that's called a wide large scale structure survey, and then another that's an ultra deep survey. And so they're going to try and get more back at the formation and evolution of structure in the universe, like David was talking about.
Okay, cool. Well, guys, we are. It always goes fast. I always think, if we ever, every time we do a hangout, I always say, well, if we, we'll just stop if we run out of things to talk about. We've never, ever done that once yet. So, I want to thank you guys so much for taking time out to talk with us about the Large Millimeter Telescope. My guests today were Nat DeNigris. She is at the University of Massachusetts at Amherst, and also David Sanchez, who's currently down in Mexico at the facility, or at least at the What'd you call it?
The base camp.
Base camp. Thank you.
Yeah.
Doing some observations right now on star formation at the large millimeter telescope. So, thank you guys so much. Real briefly, can you tell me? Okay, in addition to Toltec coming out online, what's the future of LMT? Is it just gonna continue operating? Are you going to expand it? Are there improvements coming? What's in store for the large millimeter telescope?
Well, right now we are basically receiving a bunch of new instruments to basically have more wavelengths surveyed by the LMT. We have the receiver I was working last night is called Sequoia, which is a 3 millimeter spectrographer. We have B4R, which is a collaboration with Japan, which is 2 millimeter wavelength spectrograph, and both of those can take image and spectrum at the same time. So these are really different detectors from what Nat was describing. These are heterodyne detectors, and we are planning to have more instruments like super spec, and then try to improve our surface, increase the accuracy of the surface to go to sublimeter wavelengths, as 850 microns will probably be beyond, because the site is able to make these observations.
Did you say below 800
well,
nanometers?
Provide that you can. Well, I didn't talk about this, but our surface is basically segmented in roughly 188 segments. And provided you can set those in the right way, and you have this lambda over 20 accuracy down to other wavelengths. So our next target is increase our efficiency to 850 microns. And then with that, we will be able to analyze and consider if we can go below that.
Okay.
There are other ideas right now, and this is also coming back to this iterative process of science. We are now having ideas on how to increase the field of view, the instantaneous field of view of the telescope, using some adaptive optic techniques, just to increase how much area we can serve with the LMT, or modifying the secondary mirror. That's all the things we are beginning to think for the next stages of the LMT.
All right. Well, that's excellent. Okay, guys. Well, lots to look forward to. Thank you again for taking time out to talk with us. I want to thank all of you guys for watching. Next week, I've got guys from Keck on. We're going to talk about a project called Panoptes, I think is how you pronounce it, but it is a citizen science initiative that allows you to take data in your backyard, submit it to Keck, and they will run an algorithm for exoplanet light curves. So this is a chance for you to get started in helping to confirm exoplanets and everything else. So you want to check that out. That's next week. Two astronomers from Keck Observatory, one from Keck, one from Subaru, will be talking about their project and how you can get involved. That's next week, and I will see you guys then. On behalf of my guests, I want to thank you so much for watching, and as always, keep looking up.